Before anyone can build a dam, they have to solve a strange problem first. You cannot pour concrete underwater across a flowing river, so the very first job in building a dam is to get rid of the river. This is called river diversion, and it is one of the biggest jobs on the entire project. On a large dam, crews bore diversion tunnels straight through the rock of the valley walls, sometimes big enough to drive trucks through, drilled and blasted out and then lined with concrete. Once the tunnels are ready, the river is forced to abandon its own bed and flow through them instead. To do that, they build cofferdams, temporary barriers of rock and earth thrown across the river upstream and downstream of the site. The upstream cofferdam blocks the river and pushes it into the tunnels. The downstream one keeps water from backing up into the site from below. Between them, for the first time in the river's history, there is a dry stretch of valley floor. That dry gap, walled off from the river at both ends, is where the real dam finally gets built. You cannot found a dam on loose river gravel or soft soil, because water will simply find its way underneath and the whole structure can be undermined. So crews excavate the entire footprint right down to solid bedrock, stripping away everything soft until they reach rock strong enough to carry millions of tons and to seal against water. Then they go further. They drill a line of deep holes into the rock along the base and pump in cement under pressure, filling every crack and fissure in the bedrock itself. This is called a grout curtain, an underground wall of sealed rock stretching down below the dam, and its whole purpose is to stop water sneaking through the ground beneath the structure. A dam that fails almost never fails by being pushed over. It fails when water finds a path underneath or around it. The most straightforward kind of dam is a concrete gravity dam, and the name tells you exactly how it works. It holds the water back using nothing but its own colossal weight. It is a giant triangular wall of concrete, thin at the top and enormously thick at the base, and the water pressure trying to push it downstream and tip it over is simply overwhelmed by the sheer mass of concrete sitting on the bedrock. That is why the base is so vast. The concrete is not poured in one go. It goes in as thousands of separate blocks in layers called lifts, each one a manageable size. And there is a hidden problem with that much concrete. As it cures, it generates heat, and a solid mountain of concrete would take decades to cool, cracking itself apart as it did. So the concrete is actively cooled, with cold water pumped through thousands of thin pipes cast into the blocks, carrying the heat away so the dam sets evenly. In a narrow, steep-sided rock canyon, engineers can use something far more elegant, an arch dam. Instead of relying on its own weight, an arch dam is curved upstream into the water, and it carries the entire load of the reservoir sideways, into the rock walls of the canyon on either side. The water actually pushes the arch tighter into its supports, the same way a stone archway in a bridge gets stronger under load. Because the rock is doing the work, an arch dam can be astonishingly thin for its height, using a fraction of the concrete of a gravity dam. But it only works where the geology is right, where the canyon walls are solid enough to take that thrust. Where there is no rock canyon at all, just a wide valley, the answer is usually an embankment dam, a vast man-made hill of earth and rock with a waterproof core of clay or concrete buried down the middle. These are the biggest dams by volume on Earth, and they hold water back the same way the gravity dam does, with overwhelming mass. Every dam needs a way to let water out safely, and this is more important than it sounds, because the single greatest threat to a dam is water rising over the top of it and eroding it away from behind. So every dam has a spillway, a controlled overflow route that carries flood water safely past the structure. On many dams, it is a great curved concrete chute called an Oji spillway, shaped to match the natural path of falling water so the flow stays smooth and controlled rather than tearing at the concrete. Big dams have gates that can be opened to release water in a measured way. And at the bottom of the spillway, there is usually a stilling basin, a deliberately built pool designed to catch the falling torrent and kill its energy, so it does not scour a hole in the riverbed and undermine the dam it just came from. The spillway is the safety valve, and it is sized for the worst flood engineers think the river can ever produce. When the structure is finished, the diversion tunnels are sealed shut, and the river, with nowhere else to go, finally begins to back up behind the wall. Filling a large reservoir can take months or even years, and it is done slowly and carefully, because the ground around a brand new reservoir is being loaded with the weight of water for the very first time, and engineers watch closely for any movement or leakage as the pressure builds. A dam is never really finished either. It is instrumented throughout with sensors measuring the water pressure inside it, the tiny seepage through it, and the minute movements of the concrete, all monitored for the entire life of the structure, which is measured in centuries. Because a dam holds back not just water, but all the energy of a river permanently, and the one thing it is never allowed to do is fail. Follow for more construction facts hiding in plain sight.